not this one. We have, yes, this one. This was the thing we were doing, and we have considered this particular tree and how C matrix can be formed. This is to show that C matrix always will not be that the summation of current of the elements of the car set is 0. That has been shown here, and that represents Kirchhoff's current law. And as we have previously seen that for the simple graph we have chosen, and for the simple tree also we have chosen, we have found the summation of Kirchhoff current basically becomes equal to the current of a particular node. And here, to show that always this will not happen, we have drawn we have chosen a different tree for the same graph, and here we have seen that this current of the element of the car set, and this is the car set. So these 4 elements are not all incident to the same node, and therefore we have seen that here also the C times IE becomes equal to 0. So therefore we can say that Kirchhoff's current law is not only valid for a particular node, it is valid for a particular zone also. In this way we have explained the result of CI equal to 0 in our previous class. Okay, and then we have formed CYBC transpose, because we have actually derived an expression for the equilibrium equation using Kirchhoff matrix, that was CYBC transpose Vt equal to CIS minus YBBS. This was the expression. Then how CYBC transpose may be explained. So if we obtain this matrix CYBC transpose, YB obviously is branch to branch admittance matrix, C is the Kirchhoff to element incidence matrix, C transpose is the transpose of that. So I have not shown the multiplication here. Later on I shall show another example there, all those steps we shall show. Okay, so CYBC transpose, if you find out, you see that this is the matrix and this is again an admittance matrix. Okay, this admittance matrix, basically you can say this is also one form of nodal admittance matrix, but or more truly you can say that this is nothing but node to node admittance matrix. Okay, or you can also say this is the Kirchhoff admittance matrix. How can we actually relate this matrix with this Kirchhoff? You see that diagonal elements of this matrix are summation of the admittance of the Kirchhoff. So first Kirchhoff, it is having 1, 3, 5, 4, these 4 elements, and the self admittance of Kirchhoff 1 is y1 plus y3 plus y4 plus y5. So sum of the admittances of the elements of the basic Kirchhoff. Similarly, for the second Kirchhoff, these are the elements 2, 3, and 5, and the diagonal term of second row, second column. This is nothing but the self admittance of Kirchhoff 2. It is y2 plus y3 plus y5. These 3 elements are there in the Kirchhoff, and y33. This one. This is the summation of elements of Kirchhoff 3, means 4, 5, 6, 7. This 4 element 4, 5, 6, 7. Okay. What is regarding the mutual terms? Mutual term becomes, you see that what is the common elements between Kirchhoff 1 and Kirchhoff 2. These are the 4 elements of Kirchhoff 1. These are the 3 elements of Kirchhoff 2. Out of these 3 and out of these 4, you see that these 2 elements are common to both. That means element 3 and 5. And you see that y3 plus y5 is the mutual admittance between Kirchhoff 1 and Kirchhoff 2. Both are positive. Now, common admittance between Kirchhoff 1 and Kirchhoff 3. This is Kirchhoff 1, this is Kirchhoff 3. Common admittance here is again, here are again 4 and 5. These are the common. Okay. And the admittance here is minus y4 minus y5. That means these admittances are coming with a negative sign, these admittances with a positive sign. Now let us see why this is happening. That means mutual admittance between Kirchhoff 1 and Kirchhoff 2 is common admittance, or admittance of sum of the admittances of the common branches, common elements, and this is coming positive between cursor 1 and 3. Common admittances are appearing here, but this is coming as negative. Now let us check why this is happening. Between cursor 1 and cursor 2, you see direction of cursor 1 is this one, because direction of the cursor is determined by the branch forming the cursor. Okay, this is the branch responsible to form this cursor, and this is the branch 2. That means three elements are called branches. This is a tree element. This is responsible for the formation of cursor 2. Now this is the direction. That means direction of this cursor is towards node 2. Direction of cursor 1 is towards or away from node 4. Better to say that from right hand side of this line to the left hand side of this line, and also for this one from the right hand side. If I stand on this line, on this arc, then you can say from the outer side to the inner side, or from the right hand side of this graph of this arc to the left hand side. That means if I stand here, then the direction is from right hand side to the left hand side. Okay, now you see that direction of cursor is from outer to inner side of this arc. Direction of this cursor is from the right hand side to the left hand side of this line. Now consider element 5. What is its direction? 5 is common to both cursor 1 and cursor 3. Okay, cursor 1 and cursor 3. This is 5 is common. So who is the direction? For cursor 1, it is opposing the direction of the cursor 1. Direction of element 5 is opposing the direction of cursor 2. But direction of element 5 is towards the direction of cursor 3. That means direction of element 5 is against the direction of cursor 1, but towards the direction of cursor 2. That means its direction is opposite with respect to the two cursor. That's why its admittance has appeared as a negative admittance, minus y5. Similarly, see what is happening to y4. This is y4. The direction of y4, it is outgoing, it is from moving from right hand side to the left hand side of this arc. Okay, so with respect to cursor 3, its direction is opposite. What is happening with respect to cursor 1? It is towards the direction of cursor 1. So element 4, it is opposing the direction of cursor 3 but assisting the direction of cursor 1. Then in the two cursors, its directions are in opposite nature. That's why it is also coming as a negative admittance. Now consider common admittances between cursor 1 and cursor 2. This again, this y5 is a common admittance and y3 is a common admittance. What is happening to y3? Y3 is towards the direction of cursor 2, and this is against the direction of y3 is against the direction of cursor 2 because it is inward, it is outward, and y3 is again against the direction of cursor 1. Okay, so y3 is having the same direction with respect to cursor 1 and cursor 2. Both are opposing. That's why, since direction are same with respect to both the cursors, this admittance is appearing as a positive admittance, y3. Similarly, what is happening to y5? y5 was having opposite direction with respect to cursor 1 and cursor 2. But what happens in respect of cursor 1 and cursor 2? In respect of cursor 2, it is opposing, outgoing from the left to the right. But cursor is from the right to the left, opposing. With respect to cursor 1, again it is opposing. So opposing in both the cursors. That's why it is appearing to be a positive. So we can actually again compare this with respect to this one. Say y5, cursor 2 and second row and third column. That means mutual admittance between cursor 2 and cursor 3. See what is the mutual between 2 and 3, cursor 2 and cursor 3. This is cursor 2, cursor 3. Common is the element 5. What is the direction? Direction of element 5 and direction of cursor 3 same. direction of element 5 and direction of cursor to opposite. So opposite with respect to the two cursors. Okay, that's why it will be minus y5. So it is minus y5. Okay, so you see that this is how we can explain the or we can actually explain the meaning of the elements of the admittance matrix that we have formed by multiplying C with YB and then with transpose of C. This gives an admittance matrix. This admittance matrix, you can say it is cursor to cursor admittance matrix. Self admittances are summation of the admittances of the element of the cursor or basic cursor. Mutual admittances are the common admittance between the two cursors. Mutual admittance will be positive if the direction of the element is same with respect to the both cursors, and it will be minus negative if the direction of the element is opposing with respect to the two cursors. Okay, one is assisting, one is opposing. Okay, this way it is opposing. All right, so this is the physical meaning, we can say. So now, do any question up to this? Then I shall move to that B matrix and A matrix. Okay. Any question up to this?
স্যার স্যার বলছি মানে কমনটা কিভাবে বলছেন, মানে দুটো কাট সেটের
দুটোর কমন মানে এই মানে ধরো y5 মানে এলিমেন্ট 5 এটা কাট সেট 1 এও আছে 3 তেও আছে, কাজে y5 is common to both কাট সেট 1 and কাট সেট 3. ওকে,
আচ্ছা আচ্ছা, মানে মানে হচ্ছে কাট সেটটা যেগুলোকে কাট করছে, দুটো কাট সেটই যেগুলোকে কাট করছে।
হ্যাঁ, মানে y কাট সেট 1 এ তো 4টে এলিমেন্ট রয়েছে, কাট সেট 3 তে 4টে এলিমেন্ট রয়েছে। এই 4টে এলিমেন্টের মধ্যে দুখানা এলিমেন্ট কাট সেট 1 এও আছে, কাট সেট 3 তেও আছে। কোন দুখানা এলিমেন্ট? 4 and 5, these two elements. Okay, and these two will appear in the as the common admittance between the two cut sets. Similarly, cut set 2 তে রয়েছে 3টে এলিমেন্ট, কাট সেট 1 এ রয়েছে 4টে এলিমেন্ট। এই 3 আর 4 এর মধ্যে কমন কোনগুলো? কমন হচ্ছে 5 আর 3,
3 and 5.
3 and 5, they will appear as the common admittance between cut set 1 and cut set 2. আর 2 আর 3 এর মধ্যে কমন রয়েছে কোনটা? only element 5. So this will appear as the common admittance between 2 and 3. Okay, once this is understood, then regarding the sign, self admittances always will be positive and mutual admittance will be positive if the common admittance is having same direction with respect to both the cursors, and it will have a negative sign if the common admittance is having opposite direction with respect to the two cursors. Okay, all right, clear?
Yes sir. স্যার আরেকটা জিনিস ছিল, সেটা হচ্ছে মানে এখানে যেমন কাট সেটের যেটা নেমিংটা করেছেন না, মানে রোমান 1 রোমান 2 রোমান 3 দিয়ে সি ম্যাট্রিক্সটা যখন ফর্ম করছেন, তো মানে এবারে আমি যদি ওইটা যদি যে কোনো দুটোকে যদি চেঞ্জ করি, মানে সেটা কিছু হবে না তো? মানে
নাম্বারিংটা চেঞ্জ করছো তো?
হ্যাঁ,
না না, সেটা তুমি এটাকে 3 বলো, এটাকে 1 বলো, এটাকে 2 বলো, অ্যাকর্ডিং টু দ্য ম্যাট্রিক্স উইল বি চেঞ্জড। ম্যাট্রিক্স উইল বি চেঞ্জড মানে এই রোটা, এটাকে যদি আমি 2 বলতাম এটা সেকেন্ড রোতে আসতো, এটাকে 1 বললে এটা ফার্স্ট রোতে চলে যেত, ট্রান্সপোজটাও তা ওইরকম ভাবেই হতো। মানে নাম্বার ইউ ক্যান পুট মানে অ্যাকর্ডিং টু ইউর চয়েস,
আরবিট্রারি, মানে ঠিক আছে,
arbitrary numbering will be okay. Any other confusion? Any other question, anybody?
No sir.
So then let us see the B matrix. Already we have shown that, or we have derived the expression relating B matrix. What was the expression? B ZB B transpose into I loop. This was equal to B into BS minus ZB IS. This was the expression. This was the equilibrium equation. Okay, and we have mentioned that B ZB B transpose. Obviously, it will be an impedance matrix. That impedance matrix we have written as the loop impedance matrix. Arbitrarily say we have written loop impedance matrix. Now let us see that it is actually the loop impedance matrix. Okay, So now let us therefore obtain this product BZBB transpose. Previously I have written this product to be the loop impedance matrix for this particular choice of the tree. Okay, so let us see, let us form the B matrix first and then multiply BZBB transpose. The multiplication steps I have not shown here, okay, because you can do it, but again I shall consider another example there. Some of the multiplications, though you can do it, I have shown again, okay, for further clarification. After completing this, I shall show that one. Okay. Now, this was the tree, the same tree. This tree we have chosen, and for this selection of the tree, these are the loops. You see that this is the tree branch, this is the tree branch, this is the tree branch. So remaining are the links. How many links are there? 1, 2, 3, 4. So there will be 4 basic loops. Okay. So loop 1, say let us call this as loop 1. What I have done actually, element. So this is element 2. Okay. This is element 4. Element or link having lower number, I have given a lower loop identification. So say as if this element 3 is forming the first loop, element 4 it is forming the second loop, element 6 it is forming the third loop. Okay, in this element 5 it is forming the third loop, and element 7 it is forming the fourth loop. This is why I have numbered the loops. Okay, because the dotted lines are the links, they are responsible for the creation of the basic loops, and element having lower number has been assigned the lower loop number also. Okay, this is where I have identified them. You can actually put your number according to your own choice, no problem. Any number you can choose. Simply the row and row will be interchanged in this case, nothing else. Okay. So with this, you know how to form this loop impedance matrix. Here will be the loops, here will be the elements. So for element 1, say element 1, it is in loop 1. Okay.
স্যার স্যার লুপগুলো আরেকবার বলবেন, মানে বুঝতে পারলাম না ঠিক করে ডায়াগ্রাম।
You see, this is the tree, right? Farm lines are representing the tree elements, element 2, element 1, and element number 6. I have chosen this as the tree elements. Okay, there are 4 nodes. So in the tree there will be 3 elements, number of nodes -1, 3 elements. So okay. Element 2, element 1, and element 6 are considered to be the branch of the tree that we have chosen. Okay, so remaining elements will be the links. All right, so this element number 3, this is the link, and when you add this element 3, this is the loop you are getting. 1, 2, and 3. This is the loop. This is the first loop. Okay, this loop has been given the number, assigned the number 1. Okay, then element 4, as soon as you add element 4 with this tree, then you are getting this as the loop. In this loop, remember that in the basic loop there will be only 1 link and remaining will be 3 branches. Okay, that's why element 4, element 1, element 6, these 3 elements are considered to be forming the loop number 2. Okay,
loop 2 টা আরেকবার মানে বুঝতে পারলাম না, loop 2 টা
loop 2 হচ্ছে element number 4, then element number 1, then element number 6. এই আউটার লুপ। আমাদের কার্সারটা দেখো, এই যে কার্সারটা মুভ করছে, this is the outer loop. কেন না আউটার লুপটা বলছি, কারণ এই আউটার লুপের মধ্যে একটাই মাত্র লিংক রয়েছে। ওকে, this element 4, remaining are element 1 and element 6, they are 3 branches. তাহলে loops where there will be only 1 link is called a basic loop. আমাদের উদ্দেশ্য হচ্ছে বেসিক লুপটাকেই শুধু আইডেন্টিফাই করা, that will be utilized or that is useful in the solution of network using loop impedance matrix. বুঝতে পেরেছো? তার ফলে আমরা এটাকে লুপ ধরছি, আমরা তো অন্য কোনোটাকেই লুপ ধরতে পারতাম। 4 to 5 মিলে একটা লুপ হতেই পারত, কিন্তু সেটা লুপ হবে, বেসিক
বেসিক হবে।
Okay. Similarly, element 5. তুমি যখন element 5 ধরছো, then what is the loop? Element 5, element 6, element 1, element 2. These 4 elements together will form the basic loop. Okay. See, this has been shown in this way. Okay. Then element 7. Element 7 যখন ধরছি, then the loop is very simple, consisting of
6, 7.
element 6 and 7. Okay. So accordingly, this matrix has been formed between the loops and the elements. Okay. Loop 1, ধরা যাক element 1, it is in loop 1, it is in loop 2, it is in loop 3. So element 1 is in all the three, in the first 3 loops. In the first loop, it is having the same direction, so +1 here. In the second loop, this is the direction of the loop, so it is having the opposite second loop direction. This is the direction of the second loop, and direction of the element 2 is same because direction of the element 4 আমরা element 2 এরটা কনসিডার করব আপাতত। তো 2 এরটা যখন কনসিডার করছি তখন কি হচ্ছে, element 2 this is in card set in loop 1, then element 2 is in this loop, that means third loop. Then in 1 and 3, this loop is having any participation. So in case of element 2, it will be in 1 and 3 and positive in both the direction. Okay. In
Yes,
both the
sir.
direction. Element 3. Element 3, where is the element 3? This is element 3. Element 3 has formed the loop 1, so it will be taking part in loop 1 only, and obviously it will be positive. It will be positive. Element 4. Element 4. This is forming this loop. Okay. This loop. That means element loop 2 is formed by element 4. Since it is a link element, so obviously it will be in loop 2 only, in one loop only, and that is in loop 2. Element 5. This is element 5. Again a link. So it will be taking part in one loop. That means in loop 3. Loop 3. Element 6. It is taking part in this loop and this loop, and in this loop. That means it is taking part in loop 2, loop 3, and loop 4. 2, 3, and 4, and it is shown to be the opposite sign in all the loops. Direction of the loop is direction of the element is in this direction. Then element 6, direction of the element is in this direction. Direction of the loop, this is loop.
সেকেন্ডটার জন্য তো স্যার যে +1 হতো না, 2?
হ্যাঁ, সেকেন্ডের জন্য +1 হতো, sorry, it is minus shown here, but obviously it will be plus. Okay, because the same, and the same. সেকেন্ডের জন্য এটা হবে প্লাস হবে, so the correction will be needed there. So this is the direction of the loop, and this is the direction of the element. So for this case it will be +1, and an error is there, so it will be +1. Remember this. Then for the loop 3, where is loop 3? This is loop 3 in the opposite direction, -1. Loop 4 in this direction, -1. So it will be plus here, minus here, and minus here. Okay. So then if you multiply now BZB B transpose, so if you obtain BZB B transpose, then you will have this matrix. We shall check whether this is correctly written or not, because since there is an error here, minus plus has been minus here, so there may be error introduced here also. Let me check. Okay. So BZB B transpose, perhaps this will be the matrix, and this obviously is an impedance matrix because B and B transpose are having 1 and 0 only. 1, 0, -1, all this. So diagonal terms of this matrix, how many rows and how many columns of this matrix BZB B transpose? There will be 4 by 4 matrix because there are 4 loops. Okay. So this is the self impedance of loop 1. See, in loop 1 there are 1, 2, 3, these 3 elements, so summation of impedances of these 3 elements, Z1 plus Z2. In loop 2, this is loop 2, elements are 4, 1, and 6, 1, 4, and 6, summation of all these 3 impedances. In loop 3, this is loop 3, element number 5 is forming loop 3, so that means 5, 6, 1 and 2, 5, 6, 1, 2. So 1, 2, 5, 6. Similarly, loop 4 is 6, 7, summation. Okay. Now the mutual impedances between loop 1 and loop 2. Between loop 1 and loop 2. This is loop 1 and this is loop 2. So here the loops are not as simple as the loops we have formed previously while we have considered the loop form of analysis. Okay, there we have selected very simple loop. Okay, all are having the positive direction or clockwise direction. Now the direction is not positive. Okay, we have determined the direction using the procedure of the graph theory. Okay, now you see that common impedance between loop 1 and loop 2. What is the common impedance, or what are the common impedances? This is loop 1,
Z1,
this is
only
element to
element
loop
1.
2, only 1. Then what is the direction of loop 1? It is in what is the direction of loop 2? In this direction. So direction of element, this element is actually same as loop 1 but opposite to loop 2. So direction of the element is opposite in the two loops. That's why it is minus. Similarly, Z1
স্যার এটা আরেকবার বলবেন
loop element
কমন
loop
হচ্ছে
1
1
common impedance. Common impedance, which one is common? Common
1
impedance is 1. Okay, so impedance between loop 1 and loop 2 is Z1. Now the sign. Direction of loop 1 current is this one, same as the current in element 1. What is the direction of loop 2 current? In the opposite direction. So direction of the current through this element is opposite for the two loops. Okay, direction of current through this element is opposite for the two loops. That's why it is appearing as a negative impedance. Now between 1 and 3, between loop 1 and loop 3, this is loop 1 and loop 3, this is loop 3. So what are the common? In loop 1 we have
One and
Z1 and Z2. These are the common impedances, so it is Z1 plus Z2. It is written to be positive here, but see whether it is positive, should be positive or not. You see that Z2, okay, it is Z1 and Z2. Now first of all consider Z1. Through Z1, this is the loop current of loop 1, this is the loop current of loop 3. So through element 1, both the loop currents, that means current of loop 1 and loop 2, they are in the same direction, so it should be positive impedance. Through impedance or through element 2, this is the direction of loop current, this also is the direction of the loop current, both are in the same direction, so that is also positive. That means through this element both the loop currents are in the same direction, so it is appearing to be positive. Between loop 1 and loop 4, this is loop 4, there is no common branch, so that is 0. Impedance matrix is a symmetric matrix, so Z12 will be equal to Z21, Z13 will be equal to Z31, Z14 will be equal to Z41. Okay, now let us come to this one, Z23. Between loop 2 and loop 3, what are the common? Between loop 2, this is loop 2 and this is loop 3. What are the common? Common are loop 2, 1 and 6, they are common. Between loop 1 and loop 2,
Yes, sir.
1 and 3, they are 1 and 6, they are common. So Z1 and Z6, so Z1 and Z6 are there. Now the sign of Z1 and Z6 here. So between loop 2 and loop 3, loop 2 current through impedance 1, it is against the direction of the element, okay, and loop 6 is in the same direction of the element. Okay, loop 3 current is in the direction of the element, loop 2 current is against the direction of the
minus Z6 হতো
minus Z1. Loop 3 current through Z1 is in the same direction, loop 2 current through element Z1 is in the opposite direction, so it is minus Z1. Loop 6 current, how it is?
Minus
In loop 6 is in the same direction and loop 3 in the opposite direction, so it should be minus. Actually it should be minus. Okay, so that is because it is actually wrongly mentioned minus, so that has been here also, it has become wrongly it has appeared here. So okay, so it will be minus Z1 minus Z6. Actually here it is positive, so it will be minus Z1 minus Z1 minus Z6. That means here it will be also be minus Z1 minus 6. So a wrong entry here, in place of -1 it will be +1. Okay, then this one 2 4, loop 2 and loop 4, this is loop 4 and this is loop 2. Loop 2 current is in this direction, loop 4 current is also in the same direction, opposite direction, so again it will be minus. Okay, because of this erroneous entry here, we have error here also, it will be minus Z6. Okay, so it will be minus Z6 here. Is it clear? You see that this loop 2 current in the same direction as element 6, but loop 4 current is in the opposite direction, so it will be minus Z6. This is the common impedance, so it will be minus Z6, but it is appearing positive because in the multiplication the effect of this minus sign has appeared. This is the problem. Okay, because of wrong entry here, it has become positive here, but actually this should be positive here, that's why it will be negative here. It also should be negative here, it also should be negative. Okay, now see this one. This is, so the correction is needed here, correction also is needed here. Now considering 3 and 4 element, loop 3 and loop 4, what is the common? 6 is common. Loop 3 current is opposing the element current, loop 6 current is also opposing the element current, so it is positive Z6. All right, therefore here also it is positive Z6. So this will be negative, actually this will be negative, this will be negative, this will be negative, and all this sign error has been actually introduced because of the introduction of this error here. In the -1 actually will be +1 here, because I've wrongly actually noted written -1 here. Okay, so this correction will be needed. I shall make this correction and then send you. All right, is it clear? That means self-impedance of the loop impedance matrix will be summation of all the impedances, all the branch impedances, summation of all the impedances of the branch participating in the loop, and mutual impedance will be the common impedance between the two loops. The mutual impedance will be positive if the direction of current of both the loops are in the same direction. That means both the loops are having same direction current flow through the element, then it will be positive impedance. But if one of the loop is going in one direction, other loop current is in the opposite direction, that means if the currents are in opposite direction, then impedance also will be negative. Is it clear? So this direction concept is basically same as we have actually seen in case of the Carset matrix. Okay, is it clear? Bolo, any question here?
স্যার বলছি যে এইখানে মানে ব্রাঞ্চ কারেন্টটা দেখে তো কনসিডার করা হচ্ছে না, তাই তো? মানে শুধু লুপ কারেন্ট দুটো দেখে আমরা ডিরেকশন নিচ্ছি।
হ্যাঁ, লুপ কারেন্ট গুলো ডিরেকশনটা কি আছে? লুপ কারেন্ট ডিরেকশন থ্রু দ্য ব্রাঞ্চ, are they in the same direction or are they in the opposite direction? If they are in the same direction, then impedance will be positive. If they are in the opposite direction, then the impedance will be negative. Okay, এবার সেটা তুমি তাহলে বলতে পারো যে তাহলে ব্রাঞ্চ কারেন্টের ওরিয়েন্টেশনটা কোথা থেকে আসবে, সেটা পরে আসবে when we consider the incidence between the relation between the loop current and the element current. Okay, সেখানে ডিরেকশনটা চলে আসবে. All right, there we will get the direction. Okay, loop current এবং element current এর মধ্যে রিলেশন, সেখানে সেটা ঢুকবে। আপাতত এখানে যখন ম্যাট্রিক্স ফর্ম করব, then the mutual impedance এর ক্ষেত্রে you will have to consider the direction of the two loop currents to the common impedance. Okay, একটা আমি যখন দুখানা লুপের মধ্যে মিউচুয়াল ইম্পিডেন্স কনসিডার করছি, then that impedance is actually common to both the loops. তাহলে I shall have to say that to see how those loop currents are flowing through that common impedance. If they are flowing in the same direction, then it will be positive impedance. If they are flowing in the opposite direction, then it will be negative impedance. Okay.
স্যার তার মানে যদি একটা ব্রাঞ্চ কারেন্টটা একদিকে হয় আর লুপ কারেন্ট দুটো সেম ডিরেকশনে হয় কিন্তু ব্রাঞ্চ কারেন্টটা অপোজ করছে, তখন কি ওটা পজিটিভ?
তাহলে পজিটিভ হবে।
আচ্ছা স্যার।
Okay. As we have seen here, all right. সেখানে একটা এরর রয়েছে, this is actually plus. So in the multiplication, therefore, we have seen that some error has been introduced because of this erroneous sign here. Actually, you have not noted that actually this is because of actually it was somewhat clumsy. So this is the loop current and this is the direction of the element, that is opposite, same. So this and this are actually same direction, so it will be plus here. But wrongly it has been noted minus. Okay, because of that there is an error correction record here, correction record here, correction record here, and correction record here. Okay, all right. Now similarly here only we have shown the C and B matrix. Now A I have not shown here because A is rather simple, because you have to multiply A y B A transpose, but I have considered the initial tree that I have considered before. Okay, for the initial tree we have chosen, let us see how it will appear. Okay, now see this one. Okay, so this was the, if you remember, this is the initial tree I have chosen, and we have considered the cursive matrix like this. Then loop impedance, loops are formed like this. Now let us see what is the different matrices and what we get if we multiply A YB and A transpose, B ZB and B transpose, C YB and C transpose. Okay, so if you remember that this is the same matrix that we have written before, I have rewritten here for this tree we have chosen previously. Okay, so this is the graph, this is considered to be the tree, and this is the A matrix. Already we have shown this one, we have developed this one. Now I have rewritten this here because I want to multiply A YB and A transpose and see what is the matrix we are getting. Okay, so it is A YB A transpose. So say you write this matrix to obtain A YB A transpose. I should have to write here, for because the space is not sufficient, I have simply written A here, because during multiplication I shall write the full matrix here. So it is A and YB. YB basically is a diagonal matrix because we are assuming that there is no mutual term. Okay, there is no mutual impedance, there is no mutual admittance also. This is our assumption to keep the analysis simple. To keep the matrix simple, we have considered this, but later on we shall see we can include mutual impedances also, mutual admittances also, that we shall consider. Okay, so this is YB, basically a diagonal matrix. Each element is having only the self admittance, that is for element 1 it is Y1, say element 2 Y2, element 3 Y3, in this way element 7 admittance is Y7. This is what we have written here. Okay, then A transpose, you write the transpose of this A matrix here. So this row will be the first column, second row will be the second column, third row will be the third column. See whether we have any error has been introduced while writing this, rewriting this. -1 1 0 -1, -1 1 0 -1, then 3 zeros, then 0 -1 1 0 1, 0 -1 1 0 1, and then 0 0, then 0 0 1 0 0 0 1, then -1 -1 -1 -1 -1. Okay, so first of all you have to multiply these two. Let us write the product here, and I shall be rewriting A matrix here. So if you multiply this matrix by this one, then this will be the results. You match this whether you are whether it is correct or not. You please check this. This diagonal matrix has to be multiplied by this matrix, that means A transpose. Then probably we will get this matrix. To verify this whether it is correct or not, can you can see this perhaps? So if you can see this, so you check whether this product or this multiplication is correctly written here or not. First row and then first column. Actually, there are 6
Yes, sir,
zeros
ठीक है.
here. Okay, we are getting this one. All right. So product of
Sir.
YB A transpose is written here, and then
স্যার স্যার বলছি ওই ওয়াই ম্যাট্রিক্সটা যেটা ওটা তো মানে বাকি মানে ওই Y1 1 আর 2 এর মধ্যে তো ওইগুলো তো সব জিরোই ধরে নিচ্ছে তাই তো?
সমস্ত জিরো, আমি অতগুলো
হ্যাঁ।
জিরো লিখছি না আর কি, এখানে সব ব্ল্যাঙ্ক মানে all are zeros.
ওকে
And any blank space here is actually zero. I could put a big zero here, put big zero here. That would make the thing more clear. Okay, basically there is a zero here. That there are zeros here. So to represent that, I could have written a big zero here. Could have written a big zero here. That means these are the diagonal terms, and there is no mutual coupling. So all elements will be zero. That means there are 6 zeros, 1 zero here, then here 5 zeros, 2 zeros here, and there are 4 zeros, then there are 3 more zeros, 2 more zeros like this. Okay,
ওকে
is it clear? Then you multiply A with this product YB A transpose. So this row with this column written here, first row with second column multiplication written here, first row with third column multiplication written here, then second row with first column, this is the product, second row with second column, this is the product, second row with third column, this is the product. Similarly, third row with first column, the product, third row second column, and product is minus y by third row third column, product is this. Okay, so AYB A transpose would give this matrix. You check whether this multiplication again is correct or not. ঠিক আছে? All right. Now here you see that we have written the reduced incidence matrix because in nodal analysis we need not consider the reference node, because at the reference node potential of reference node with respect to reference node is 0, so that node need not be included in the matrix. That's why though there are 4 nodes, node 4 is considered to be the reference node, and there we have written the matrix for the 3 nodes, node 1, 2, 3, and all these 7 elements. And as the product, we have got a 3 by 3 matrix. That means node 1, node 2, node 3, node 1, node 2, node 3. So this is the self admittance of node 1, self admittance of node 2, self admittance of node 3. You see that this particular admittance matrix is what we actually observed, what we actually got while we considered the, or while we have analyzed the, performed the nodal analysis in our previous classes. Okay, there, this is node 1, node 2, node 3. How to form the nodal admittance matrix? Sum of all admittances meeting at this node means y1 plus y2 plus y4. Here also we are getting that. Second node, what will be the self admittance? Sum of this one, and this one. So 2 plus 3 plus 5, 2, 3, 5. And here, these are the 4 elements connected to node 3. So summation of y4, y5, y6, and y7. This is the self admittance of node 3. What is the mutual admittance between node 1 and node 2? This is the common admittance between the 2 nodes. Okay. common admittance
সবগুলো তো মাইনাস হবে।
এটা মাইনাস হবে as before here এখানে কিন্তু কিছু চেঞ্জ আর করছে না। Similarly between 1 and 3 this is the common admittance with a negative sign. Also we have seen that this has happened in case of the our previous analysis also. So this matrix is identical with the admittance matrix we got previously. Now again it is a symmetric matrix, so y12 will be equal to y21. Then see what is y23, second row and that second node and third node. Okay, between these two nodes, this is the admittance connected 5 with a negative sign minus y5. So 2 3 y23 is minus 5. So similarly y32 also will be minus 5 and 3 3 already we have seen. So this product AYB transpose, we have previously written this to be the nodal admittance matrix. So I note, and here we have seen that we have verified that this is actually the same matrix, the nodal admittance matrix, taking node 4 as the difference. Okay, all right. So there is no change. You see that in this case, using graph theory and using simple observation, by observing we have formed one admittance matrix previously. Now here we have formed the admittance matrix using the graph theory. There we are obtaining the same admittance matrix. Okay, because node will not change, node remains node. But what happens in case of loop impedance matrix? It is somewhat changed. Why it is changed? Because loops we are actually selecting differently here. In the previous case we have observed, and some loops were very much clear. Then accordingly we have formed the loops, and we have assumed that loop currents are all in the clockwise direction. That gave us some advantage. But here what to do, because we shall be using, when we will actually be using the graph theory for network analysis, the network will be rather large network. It will not be a small network, because in case of small network you will not have much advantage. Okay, advantage of graph theoretic process will be obvious if you consider a large network. And in case of large network, you will not be in a position to observe the network to identify the loops. That will not be easy. Okay, so a step is systematic procedure is needed, and graph theory is offering that systematic procedure. What is that systematic procedure? Systematic procedure to draw the graph, give orientation of each of all the elements, and then to select it. So as you are selecting the tree, you are selecting the loops also, because all other elements excepting the three elements will be the links, and they will be associated with some loops. Those loops are called the basic loops. Okay, and for those basic loops we shall be forming this B matrix. So this B matrix we have formed for the this particular tree selection, and this B matrix we have shown previously also. Now let us see what this BZB transpose gives us. This is B, ZB as before as the admittance matrix, or again will be a diagonal matrix, because there is no mutual impedance. So ZB also is a diagonal matrix. So if you now multiply B, ZB and B transpose, then this perhaps will be the matrix you will be obtaining. So for these loops, these are the loops. These are the loops. For these loops, you will be obtaining this impedance matrix. What you have obtained here, let us again match this impedance matrix with this particular loops. In this case, self impedance, there is no confusion here. Summation of the elements of the loops. For the first loop, 1, 2, 3. For the second loop, this is the second loop. Now it is somewhat shorter in this case because of the particular selection of the tree. This is the loop now. Okay, 2, 5, and 4 summation. Loop 3, this is the loop. Again, a short loop is obtained. 3, 5, and 6. 3, 5, 6. And fourth loop is rather big here, rather large. It is 3, 5, and 7. Okay, 3, 5, and 7. What regarding the mutual impedance between loop 1 and loop 2? This Z2 is the mutual, but both loop 1 current and loop 2 current are flowing in the same direction through the element. Thus, Z2 is
Plus
positive. Okay. Now loop 1 and loop 3. Both loop 1 current and loop 3 current are flowing in the same direction through element 3. That's why it is a positive impedance. Between loop 1 and loop 4, again common is 3. Loop 1 current and loop 4 current are again flowing in the same direction. So that is positive. Alright. And Z12 is equal to Z21, Z13 equal to Z31, Z14 equal to Z41. Okay. Now come here. Z23, second loop between second and third loop. Second loop is this one, third loop is this one, common impedance is this one, impedance element 5 is the common. Through this common impedance, that means Z5, this is the direction of the loop 2 current, this is the direction of the loop 2 current. So currents are in the opposite direction, so Z5 will be negative. Okay, Z5 will be negative. Similarly, so Z25 is minus Z5, Z23 is minus Z5, Z32 also minus Z5. Now what is Z24? Second loop and fourth loop. This is the second loop, this is the fourth. Again common is Z5. Through Z5, this is the direction of the loop current 2, this is the direction of the loop current 4, opposing direction, so it is again minus Z5. Okay, so Z24 is minus Z5, Z42 also minus Z5. Now Z34, this one, third loop and fourth loop. This is the third loop and this is the fourth loop. Third and fourth loop, common impedances are rather 3 and 5, Z3 and Z5. Z3, through Z3, loop 3 current is in the same direction, loop 4 current also in the same direction, so Z3 will be positive. Okay, Z3 positive. And Z5, through Z5, loop 3 current is in the opposite direction of the element, loop 4 current also in the opposite direction of the element, so Z5 is also appearing as a positive impedance. Okay, both the loop currents are opposing the element current, so direction of the loop currents are same with respect to the element. That's why it is appearing as a positive impedance. All right. Similarly, since this is Z34, Z43 also same, and this is Z44. Okay. So this is how you will be forming the loop impedance matrix. Obviously, this loop impedance matrix is not as simple as the impedance matrix we obtained while forming the loop impedance matrix by inspection only. Why it will not be so simple? Because actually we are using a process here, step-by-step process. That step-by-step process will give you advantage when you are actually forming or you are dealing with large network. There, by observation, you will not be in a position to identify the loops at all. Okay, so for small network, obviously, বলো।
হ্যাঁ বলছি, মানে যদি যে বড় নেটওয়ার্ক হয় তাহলে তো আমাকে যে বি ম্যাট্রিক্সটা ফর্ম করার সময় তো যে প্রত্যেকটা লুপকে তো হচ্ছে ওই চেক করতে হবে, +1 বা যে -1 এর ভ্যালুটা এ করার জন্য, তখন তো আমাকে মানে যে পুরো নেটওয়ার্কটাই তো যে দেখতে হচ্ছে, তাহলে তো মানে কি সুবিধা?
বড় নেটওয়ার্ক যখন তত বড় নেটওয়ার্ক হবে তখন এইটা কি তাহলে তখন তুমি আর লুপটা তো দেখে ফর্ম করবে না, লুপটা অটোমেটিক্যালি ফর্ম হবে, and you will be basically you have to manual process, you have to avoid, you have to write some program to identify the direction. Okay, এটা তো প্রোগ্রাম করতে হবে, you will be writing the code, সেই কোডের লজিকটা তুমি ঠিক করবে, that logic is explained here. কেননা ধরো একটা নেটওয়ার্ক আছে যাতে 100টা নোড আছে, 100টা নোড ধরা যাক there are 150 elements, then how many loops will be there? So can you actually inspect the network and identify the loops for such a big network. Drawing the network will be some difficult, but in তোমার খাতার পাতায় তো তুমি অত লেখে এঁকে উঠতে পারবে না অত কোটা লুপকে, বুঝতে পেরেছো? So there you have to follow some other technique. What will be that technique? Obviously you have to use some computational technique in that case. So you will be putting your logic into the program, and the program will then determine what is the direction, what is the loop. The program will actually put 1 or -1 on 0. Okay, so that has to be done in that way. তাহলে বলতে পারে যে obviously this graph theoretic procedure will be actually helpful when you are dealing with large network. এবার বড় প্রশ্ন উঠতে পারে, তাহলে কি অত বড় নেটওয়ার্ক কি সত্যি হয়? অবশ্যই হয়। তুমি যখন ছোট নেটওয়ার্ক তখন এটা ঠিক আছে, কিন্তু বড় নেটওয়ার্ক তুমি কোথায় পাবে? ধরো you are dealing with a power system network which is much bigger. আমি যদি 100টা নোড বললাম, একটা পাওয়ার সিস্টেমের নেটওয়ার্কে 100টা নয়, there will be several thousand nodes. Okay, so তুমি 1000 একসঙ্গে যদি নাও করতে চাও, it will be 50, 60, 70, 200, 400. This will be the size of the network. Then how will you go for loop analysis? You will not be in a position to identify the loops at all. পারবেই না করতে। There will be take help from this process. Okay.
Yes, sir. Yes, sir.
Similarly, now if you form the C matrix for this simple tree we have selected, C matrix. Now you see that this is the C matrix. So it is YBC transpose will be like this. CYBC transpose will be like this. Okay, CYBC transpose like this. Now you can identify, or you can identify this with this thing actually. But it's not. These are the card set for the simple tree, and this is the C matrix. I have written YBC transpose to help you actually follow the steps. I have written YBC transpose here, this product, then CYBC transpose is multiplied and the product is written here. Okay, and this is the product obtained. Now here you see that this is nothing but the sum of elements of the card set, admittance of the card set, sum of admittance of the card set, sum of admittance of the card set. Okay, mutual Y1 appearing as positive means element 1 is common to card set 1 and card set 2, and both are having similar direction with respect to element 1. Let us verify this. Element 1 is common to both card set 1 and card set 2. Direction of card set 2 is in the opposite to element 1. Direction of card set 1 is also opposite to element 1. So both are having same direction. Both the card set are having same direction with respect to the element. So Y1 mutual admittance between card set 1 and card set 2 is positive. It is positive. Similarly, between card set 1 and card set 3, card set 1 and card set 3, this is card set 1 and card set 3. This Y4 is common. Okay, this element 4 is common. For the direction of card set 3, opposing the element. Direction of card set 1, opposing the element. So both are opposing the element current. Okay, means Y4 will be positive. Y4 will be positive. So therefore Y11, 12, 13, Y21 same as 12, Y31 same as Y13. Then this one between card set 2 and card set 3. Card set 2 and card set 3, what are the common? Card set 2 and card set 3, common branches are rather 6 and 7. What is the direction of 6? It is opposing this card set. What is the direction of 6? It is in the same direction of the card set. So Y6 will be negative. Y6 will be negative. Similarly, Y7. Y7 opposing card set direction, element direction are opposite, and card set direction and element direction are same. So Y7 also will be negative. Y7 is negative. So Y23 is minus y6 minus y7, also y32 minus y6 minus y7. Okay, and this is already explained, the summation of admittances of the car set 3. Okay, all right. So this is how you can actually form the network equation. You can have the impedance matrix, admittance matrix as the product of AYB A transpose, BZB B transpose, and CYB C transpose. Okay, is it clear? Now, any question up to this? Bolo. Now we shall go for.
হ্যাঁ স্যার বলছিলাম ওই মানে হচ্ছে যে আগের কেসে হচ্ছে আমরা যে ট্রিটা নিয়েছিলাম আর হচ্ছে এই কেসটাই যেটা নিলাম, তো ওই যে দুটোর ক্ষেত্রেই তো হচ্ছে যে এই যে বি এই বি হচ্ছে আর যে সি ম্যাট্রিক্সটা তো হচ্ছে চেঞ্জ হচ্ছে, তাই তো? আর
সি ম্যাট্রিক্স চেঞ্জ হচ্ছে, এটা চেঞ্জ হবে না, এটা চেঞ্জ হবে না। হ্যাঁ, আর রেফারেন্স নোড তো আমরা বাদ দিয়ে দিয়েছি, আমরা এটা তো রেফারেন্স নোড বাদে সবকটা নোডের মডিফিকেশন, কিন্তু কার্ড সেটের মডিফিকেশন আছে, কারণ ট্রি সিলেকশনের সঙ্গে সঙ্গে কার্ড সেটও পাল্টে যাবে, লুপও পাল্টে যাবে। অ্যাকর্ডিংলি দি ম্যাট্রিসেস এন্ড ইম্পিডেন্স ম্যাট্রিসেস অলসো উইল চেঞ্জ। ওকে, কিন্তু নোডাল অ্যাডমিটেন্স ম্যাট্রিক্সটা চেঞ্জ হবে না, বিকজ দ্যাট ইজ রিলেটেড টু দ্য নোডস। ওকে,
আর যে রেফারেন্স নোডটা যদি যে চেঞ্জ করে দিই, রেফারেন্স নোড চেঞ্জ করলে তো চেঞ্জ হবে।
চেঞ্জ করলে তো অবশ্যই চেঞ্জ হবে। সেটা তুমি যেই ট্রি সিলেক্ট করো, whatever the whenever you change the reference node, obviously the matrix will change. Okay,
yes sir, yes sir,
is it clear? কিন্তু BC matrix reference node এর সঙ্গে কোনো সম্পর্ক নেই। all right,
yes sir, হ্যাঁ ওটা তো পুরোটাই চেঞ্জ।
all right, now let us now go to another example rather, where we shall be showing a mutual coupling, how mutual coupling may be considered, and how we can form the full complete equation now. Okay, because here we have considered only the matrices, incidence matrices, and then impedances or admittances. Voltage or current sources we have not considered so far. So let us now form a total equilibrium equation, and also let us include the mutual coupling, mutually coupled element, then how that can be included in the analysis of the graph theory. Okay, now consider this one. So we shall now consider an example for solving the network using graph theory. Though the example that we are considering is very simple. It is a small network I am considering here because I want to show the procedure only. That's why it is better if you consider a small network, and if you consider a small network, then obviously matrices will be small, graph will be small, it will be very easy to demonstrate also. That's why. Okay, now assume that this is the small network, say voltage source along with an resistance. This is one branch or one element, and there is an inductor between node A and node B. Between node B and node C there is a capacitor. 4 farad is the capacitance value, 4 Henry is the inductance value. Between node A and C there is another inductor of value 2 Henry. Okay, then this is a sinusoidal source, and this element between AB and AC they are coupled. Okay, they are coupled element. Coupling is, this is the dot, this is the dot, and coupling is having some value. That value is not shown here. Okay, we shall see what is the value. Okay, so what will the first step? First step will be to form the graph. You form the graph between AC to represent voltage source with series resistance. This is the arc. Okay, between AB mutual inductor with mutual coupling, this is the line showing that element BC, another line to show BC, and between AC this line is showing the element BC. So let us number this element with voltage source and series resistance, the element 1. Between AB the element to be number 2. Between AC as the third element, between BC as the fourth element. And we are putting arbitrary direction. Say this is the direction of element 1, element 2, element 4, element 3. This direction obviously is arbitrary. You could assign a completely different direction, say upward direction here, upward here, downward here, any arbitrary direction you could put. But once you put the direction, you maintain it throughout the problem. Whenever you are solving the problem, you don't change the direction after that. Initially, you put in some direction and follow that direction. That is what is necessary. But assigning a direction is arbitrary. It is your choice. Okay. Now let us select. There are 1, 2, 3 nodes. So obviously, in the tree there will be 2 elements. So say AB, that means element number 2 and element number 4 are selected to be the 3 branches. Okay, this is forming the tree. Okay, there are 3 nodes, so 2 elements will be there in the tree. So these are the 3 branches. Element AB, that is having number 2, element BC having number 4. So now here, if we use Carset matrix, let us show the example of using Carset matrix. Okay, you could write the loop also very easily. Okay, I am showing the formation of Carset, formation of equation using B matrix or A matrix. You can easily follow that. Okay, so C matrix will be, for that is choose one Carset. This is the second Carset. Carsets are very obvious here. This will be first Carset 1, so this is Carset 2, and accordingly you form the Carset matrix. Okay, element 1 in Carset 1 and also in Carset 2, it is having negative sign in both the Carset. Okay, direction is upward. The direction is actually should be upward here. It is not. It is missing here. Okay, by mistake it has been actually missed here. Okay, so it will be upward. -1, -1. Element 2. Element 2 has formed Carset 1, so it will be in Carset 1 only, and it will be positive. Element 3. Element 3 again in both the Carset. It is positive in both the Carsets. So element 3 positive in both the Carset. Element 4 has formed Carset number 2, and in the same direction, obviously, because it has formed Carset 2, its direction is the direction of the Carset, so it is positive. So it is C, and now ZB. Here lies the trick how to form the, or how to actually include the mutual coupling, mutually coupled element. Now you see that here,
supporting.
this is the branch to branch impedance matrix. Okay, branch to branch impedance matrix. Branch 1 impedance, it is 1 ohm, and there is no mutual coupling, so 0 remaining elements are 0. Branch 2, this one, having the cell wave impedance of J4 omega. Okay, J4 Henry, J4 omega, and mutual is actually mutual coupling is 1. Okay, that is shown here. That is somewhat missing here. It will be 1 Henry. Okay, mutual coupling. So between 2 and 3, it is mutual coupling is shown here. How mutual coupling is this one? I shall explain. Okay, it is between 2 and 3. This is 3. Between 2 and 3, this is the mutual. Between 3 and 2, this is the mutual. Okay, and it is the self impedance of element 3, 2 Henry, 2j omega. Okay, because the sinusoidal 2j omega, and element number 4, there is a capacitor, so the capacitor will be -j by 4 omega, 1 upon omega c. Okay, so this is the self impedance of element number 4 written. Now regarding the mutual, you see how to, the impedance value is all right, because this is 1 Henry is the mutual impedance. It is obvious from the matrix. I have actually missed to write this. Okay, the drawing I had to write 1 Henry to show the mutual coupling between the mutual inductance between the 2 elements, that I have missed. But in the matrix, it is apparent that it is basically 1 Henry. That's why, okay, j omega is the impedance. But why it is plus or minus, that will be determined by observing the position of the dots. Okay, position of the dots and the direction of current through the element. This current is leaving the dot. This current is also leaving the dot. Okay, this element current, this is the considered to be the direction. This element, this is considered to be the direction. You see that both the currents are leaving the dots, and the rule we have written for identifying the polarity of the mutually coupled voltage, mutually induced voltage. What was the rule we have written, or we have actually applied? That is, if both the currents are either leaving or entering through the dot, the mutually induced EMF will be assisting the self-induced EMF.
Yes.
Okay, supporting. Here, both the currents are leaving the dot, or direction of currents are same with respect to the dots. Okay, direction of currents are same with respect to the dots. Since direction of currents are same, the mutual impedance will be positive, because here we are showing the mutual coupling in the form of some impedance. While we have drawn the equivalent circuit, while we have considered the mutually coupled circuit there, the mutual coupling was shown in the form of some induced voltage. Okay, there we have represented it in the form of some induced voltage. Here we are representing it in the form of some impedance. Okay, in the mutually induced voltage, the polarity of the voltage was assisting the self-induced EMF if both the currents are having same direction with respect to the dots. Here also, polarity of the induced EMF, polarity of the mutual impedance will be positive, or are positive, if both the currents are having the same direction with respect to the dots. Here, both the currents are leaving the dots. That's why it is positive impedance. It is also positive impedance here. All right, and so on. You form the ZB admittance matrix. Y will be simply inverse of this. Simply inverse of this. To take the inverse of the impedance matrix, you will be getting the admittance matrix. So this is up to this, the admittance matrix. And how to form the VS source voltage? Source voltage. Now you see that we have a voltage source here. Again, the impedance was 1 at an angle of 0 actually. That again is missing here. Okay, so VS is 1 at an angle of 0. 0 is not written here, means it is 1 angle of 0, and there are no voltage sources anywhere in the network except this one. So all other entries in the VS vector is 0, because there is only one voltage source. What are the current sources? There is no current source in the network, so all current sources are 0. So had there been a current source, you would have entered a current value here. Say, for example, say let us assume that we had a current source between node C and here. So this is element number 4, and we have a current source here. Okay. So if the current source is direction is from C to B upward, then actually what will happen is C to B upward. Then you see that this current obviously will flow in this direction from B to C. To the internal impedance, current would have actually been flowing from B to C. That means, and this is the assumed direction of current through the element. That means this element and current source current are in the same direction. That's why that current source would have been a positive current source. Okay. All right. So that I have not shown here. So what I shall do in the next class, therefore, let me show one more example including the current source. Then it will be better, I think, for completeness that is required. That means if there is a current source, for putting the direction of the current source, whether it is a positive source or negative source, you see what is the direction of current to the internal impedance of the current source. If current source is flowing in the positive direction, that means in the direction assigned to the element, okay, then it will be a positive current source. If the current source is delivering a current opposite to the assigned direction, then it will be a negative current. Okay, that is the simple logic you have to follow. So here we have shown VS and IS, and once you have shown this, Now you can write the
ভিএস এর ডিরেকশনটা স্যার আরেকবার একটু বলবেন
current
ভিএসটা
direction হচ্ছে you have to see the direction of the current through the internal impedance of the current source. Okay, you have to see in which
ভিএস
direction the source current will flow. Will it be flowing in the direction that means the graph that you are showing a line you are representing this element with the help of a line. Okay, there will be a single line. That line basically is representing the internal impedance of the source. So there you have put a direction. That direction actually is the direction of positive current or direction of assumed positive current to the internal impedance. You have to see in which direction the current source current will flow. If the current source current is flowing in the same direction as the assigned direction, then it will be a positive current source. But if the current source current is flowing in the opposite direction, it will be a negative source. Okay,
ভোল্টেজ সোর্সেরটা স্যার একবার বলবেন
ভোল্টেজ সোর্সেরটা কি হবে এখানে যেমন হলো ভোল্টেজ সোর্সের বেলায় আমরা এই ডিরেকশন ধরেছি and this is the positive direction naturally যে কারেন্টটা ফ্লো করবে এই সোর্স থেকে that will be outgoing from this positive terminal and the same direction as this current.
আচ্ছা
That's why it
ঠিক
is.
আছে মানে ভোল্টেজ সোর্সের ক্ষেত্রেও যে কারেন্টের ডিরেকশনের রেসপেক্টে করব আর কারেন্ট মানে সোর্সের
হ্যাঁ।
ক্ষেত্রেও যে কারেন্টের ডিরেকশনের
current direction respect. All right. Okay, is it clear? তাহলে এইখানে ফর এক্সাম্পল দেখানো হলো হাউ টু ইনক্লুড দ্য মিউচুয়াল এইবার কারেন্ট সোর্স ভোল্টেজ সোর্স
Sir.
কিভাবে কনভার্ট করবে বলো
স্যার বলছি এখানে যেটা মানে ইম্পিডেন্স যে ম্যাট্রিক্সটা করেছেন না ওটা তো 3x4 কেন ওটা তো 4x4 হওয়ার কথা
কোনটা
ZB ম্যাট্রিক্স এটা
ZB ম্যাট্রিক্স কোনটা বলো তো এইটা
হ্যাঁ
হ্যাঁ 4/4 হতো
ইয়েস স্যার 4/4 হতো
1 2 3 4 সো ফোর্থ এটা একটা এখানে আবার একটা মিসিং হয়ে গেছে এই যে সময়টা কেন বাদ পড়লো জানি না এই একটা রয়েছিল
ও আচ্ছা হ্যাঁ ঠিক আছে
সেটা এখানে মিসিং হয়েছে কোনো একটা বার বেসিক্যালি দিস ইজ ZB ইনভার্স অফ ZB is okay
আচ্ছা
inverse of ZB is this one. So basically কোন একটা এলিমেন্ট বাদ দেয় the first row then second this second third and fourth এর বেলায় কি হতো fourth টা মিসিং হচ্ছে সরি এটা হবে তাহলে it will actually be 0 and this will be here এটা জাস্ট উপর নিচে হয়ে গেছে লিখতে সময় this is
Yes,
minus
sir.
4 by j omega is actually here it will be 0 and there are 3 zeros this is actually here okay এটা একটু নিচে নেমে গেছে যেটা এটা আবার শিফট হয়ে গেছে লেখার সময় গন্ডগোল হয়ে গেছে 0 j omega j omega then 0 here 0 0 minus j by 4 omega okay 4/4 matrix minus j by 4 omega it has been actually তাই লেখার সময় এটা তুম করে এখানে একটা মিসিং হয়ে গেছে এটা আসলে তিনটে 0 হয়ে minus j by 4 omega হবে আর এইখানটা একটা 0 হবে okay so in the inverse again it is all right ঠিক আছে এই কারেকশন গুলো ঢুকিয়ে দিতে হবে আর কি তোমাদের আমি again I will actually include this correction and send you
স্যার আরেকটা জিনিস মানে এবারে মানে এখানে যেটা ফিগার 4.2 তে যেটা আমি 40.2 তে যে গ্রাফটা এঁকেছেন না
হ্যাঁ
স্যার আমি যদি এখানে মানে ধরুন মানে অরিজিনালি যদি সার্কিটে বি থেকে সি তে একটা যদি কারেন্ট সোর্স যেটা অ্যাপ্লাই করি মানে সেটা যদি আপওয়ার্ড ডিরেকশনে হয় তাহলে তো মানে ওটা তো হচ্ছে থ্রু দ্য ক্যাপাসিটর দিয়ে ওটা তো ডাউনওয়ার্ডে যাবে তাহলে এখানে তখন ওটা
পজিটিভ হবে ইয়েস
ওকে মানে আর ভোল্টেজের সময়
আমি কারেন্ট সোর্সের জন্য যেই গ্রাফের এলিমেন্টটা দেখানো হচ্ছে they are actually we are showing the internal impedance of the source বুঝতে পেরেছো তো we are actually showing the internal impedance of the source and there the direction assigned is showing the positive direction of current through the internal impedance or assume positive direction basically আমরা এটাকে ধরছি যে এই ডিরেকশনটা পজিটিভ আমরা যে ডিরেকশনটা দিই সেটাকে আমরা ধরে নিচ্ছি this is the positive current through the element যে কোনো এলিমেন্টের বেলায় ধরো আমরা যে এই এবি রেসপেক্টে যে ডিরেকশনটা ধরেছি this is downward. That means we are assuming that in this direction current is positive for this element. For this element in this direction current is assumed to be positive. সলিউশনে এটা যে এই ডিরেকশনে আসবে তার কোনো মানে নেই, সলিউশন করলে এটা নেগেটিভ আসবে, যদি নেগেটিভ আসে তাহলে অ্যাকচুয়ালি কারেন্ট ইজ ফ্লোয়িং ইন দ্য আপওয়ার্ড ডিরেকশন। বুঝতে পেরেছো তো?
ওকে
ইয়েস স্যার।
আর ভোল্টেজের টাইমে হচ্ছে যেদিকে হচ্ছে ওই মানে অরিজিনাল ডিরেকশন অফ কারেন্ট সেটাই নেব পজিটিভ, তাই তো?
হবে, হ্যাঁ। আমি এটাকে এই ভোল্টেজের বেলায় আমি এটাকে নিচের দিকেও দেখাতে পারতাম। আমি এটা কিন্তু এর সঙ্গে কোনো রিলেশন নেই, আমি এখানে ডিরেকশন যখন দিচ্ছি I am putting it arbitrarily.
হ্যাঁ ওটা তো হ্যাঁ ওটা
that is
আরবিট্রারিলি, তাহলে তখন ওখানে ভিএস এর জায়গায় -1 হয়ে যেত।
-1.
-1.
Okay.
ওকে
Is it clear? So for completeness, what I shall do, I shall actually consider a larger network and then show all these things for that will make your understanding clear. How to include voltage source and current source. I shall include multiple voltage source. I shall consider multiple current source. Then perhaps it will be better for you to understand. So I shall give one such example in my next class. Okay. So that will actually complete our discussion on graph theory. So one more example I shall show that will complete the discussion on graph theory, and then we shall proceed to the next content. This content basically আমি এই এরপরে যেগুলো করব গ্রাফ থিওরির পরে, all those things were previously okay included in the first year course. অর্থাৎ এই সমস্ত কিছু তোমাদের ফার্স্ট ইয়ারই পড়ার কথা ছিল, and these things were covered in the first year course when common curriculum was not there. ফার্স্ট ইয়ার থেকে যখন ডিফারেন্ট ছিল তখন এটা ফার্স্ট ইয়ারই ছিল, কিন্তু ফার্স্ট ইয়ার থেকে কমন করার ফলে সবার জন্য তো সবকিছু দরকার নেই, সেজন্য ইলেকট্রিক্যালের স্টুডেন্টরাও এখন কিছুটা ফার্স্ট ইয়ারে কম করতে হচ্ছে, অন্য জিনিসও তো বেশি করছে, কিন্তু ফার্স্ট ইয়ারে কম করছে। দ্যাটস ওয়াই those things are included here. So from next class, whatever I shall discuss excepting that example on graph theory, everything were supposed to be done in the first year courses. Okay, that we shall do, and that will complete our discussion. So some of the things here will be getting maybe very easy to understand to you, for you now, because we have discussed so many other things. সেটা না করলে পরে আর একটু ছন্দপতন হতো বলে আমি এইভাবে করলাম। So there is no problem, you can understand this very easily. I can these things, and along with that we shall have to consider the nonlinear resistances. Okay, nonlinear circuit, how to solve nonlinear circuit. These things were previously included in the first year courses. So we shall go through these ones, and then that will be completing our content for this circuit. Okay. So the next class we are expectedly 2 or 3 classes.